Welcome back, everyone. We'll finish off our MNIST dataset with an artificial neural network lecture series by taking a closer look at just overall evaluation and performance on both the training set and the test set. Let's get started. All right, last time we left off, we had just run the training of our data. Let's go ahead and plot out the loss and accuracy comparisons on not just the training data, but also the validation data. We're going to begin by plotting out our train losses, and we'll give this a label of training loss. So if we just plot this out, we can see our loss is decreasing, and this is the training loss. And if I want to see a legend, I can say plt.legend, and there I can see my training loss. So we can see that as we train for more epochs, the training loss tends to go down. We do have some spikes, but overall the general trend is down. But let's compare it now to our test losses. So we have our test losses, and let's give this a label. We'll say test or validation loss. Run that, and we can see that we're not performing as well on our test and validation set as we are on the training set. And fundamentally, this makes sense. This is data that the network has never seen before. We wouldn't expect it to do as well on the test or validation set as it did on the training set, since it doesn't actually get to adjust its weights and biases based off the test set. Since, recall, we said here with no gradient. So this is information it's never seen before, and it doesn't really get to adjust to it. So in a real world situation, your test and validation loss should be higher than your training loss. But luckily, we can see that the trend is also tending to go down here, but it looks like it's leveling off after around maybe 8 or 9 epochs versus the training data still goes down. So most likely that if you kept training this for more and more epochs, you would start overfitting to your training data. And now let's go ahead and plot out the accuracy at the end of each epoch. And we can do this by taking a look at train correct and test correct. Remember, we started keeping track of these. And for training correct, due to the batch size, if we divide this by 600, if we divide each term by 600, so let's just grab one of these and divide it by 600, we end up converting that number correct to a percentage correct. So if we take a look at just train correct at 0, that's this many correct. And if we divide it by 600, then we get back the percentage correct. So what we're going to do here is we're going to create a little list comprehension that says t divided by 600 for t in train correct. And we're going to call this train accuracy. So take a look at that, and we can see our training accuracy. It goes 89, 95, 96, 97, 98, and then reaches 99. This is exactly what we're printing out here for this accuracy number. We'll do the same thing for test accuracy. So let's go ahead and say here test accuracy, except this one, due to the batch size, if you take a look at the math, you got to divide it by 100. Again, that's because of the batch size. So we'll say for t in test correct, run that. And now let's go ahead and plot this out. We'll say plot our training accuracy over time. We'll label this training accuracy. Then we'll say plt plot. We'll go ahead and say test accuracy. And let's make sure we add in that legend. So we can run this, and we can see here that our training accuracy, in a similar behavior to what we saw with the loss, the training accuracy is going to increase and get better and better as we train for more epochs until it starts to try to hit 100% accuracy. But you can see the test accuracy begins to level out. And again, that makes sense because remember, the test data is data the network hasn't seen before, and it's not allowed to really adjust its weights and biases based off of that. So eventually it will start leveling out. So you should look for somewhere around this crossing point as far as how many epochs you should really be training for. Beyond 8 epochs, you can definitely see you'll begin to get overfitting to the training data since the test accuracy is beginning to flatten out. So let's imagine we actually just wanted to evaluate the test data separately. Well, one way we could do that is we can extract all the test data at once, not even bother with a batch, just feed it all in and then pass it in through torch no gradient. And this is exactly the exact same process you would use for new unseen data. So a really common question students ask is, how can I run new unseen image data through my trained network? And this is how you do it. So again, this is new unseen data. And so I'm going to load up all the test data. Remember, that's new unseen data. And the way to do that, I'll say data loader, grab my test data, and I'll just set the batch size equal to the size of that, which is 10,000 images. And then I'll say shuffle is equal to false. And if you want, if you just want one single test point, you just say batch size is 1. But that's all my test data. And then this is how we evaluate new unseen images. We'll say with torch, no grad. We'll say correct is equal to 0. And then we'll say for x test, y test, in test load all. We'll go ahead and say yval. Let me zoom in here so we can see this a little better. We'll say yval is equal to model x test, and we're going to view it with the length of x test, which just happens to be 10,000, and then we'll say comma -1. So this flattens out all the images in x test, and then we'll say predicted is equal to torch max yval 1 index at 1, just as we did before. We can keep track of how many we got correct by comparing our predicted to where we match up with the y test values and then taking the sum of that. So if we run this, then what we're going to end up seeing is, whoops, let's make sure we have that correct as far as balance. So this would be model. There we go. Okay, so that ran all 10,000 images, had a little typo there with that period. And then what we're going to do here is, if we take a look at correct, it's currently this tensor. What I need to do is I need to grab the item from it. So just to grab that number and divide it by the number of total images we had there, which is the length of test data. So we'll say length of test data, divide that, and so we end up getting around 97.67% accuracy. So I could then times this by 100 to actually get this as a percentage. So this is our then total accuracy on the test set. And again, for new unseen data, this is all you have to do. You load up no gradient, and then you just pass into the model. So just as we did before, that's the exact same process. If you wanted to display a confusion matrix on this, what you can do is you could say confusion matrix, pass in your predicted, and we'll view this as -1, so the dimensions are right for confusion matrix, and we'll do the same thing for y test, -1, go ahead and run that, and there is your confusion matrix. So essentially, the diagonal is how many it's getting right per class versus what it's actually predicting per class. And if you have any questions on the confusion matrix, make sure to check out our lectures on evaluating classification metrics. All right. So you can check out the notebook for more details on things like examining the misses, displaying the confusion matrix, or evaluating the test data. So to bring over that notebook just so you can take a look at it. We have a in-depth discussion with code, comments, etc. on plotting these sort of comparisons, evaluating the test data, etc., displaying the confusion matrix. And if you want, you can also examine the individual misses to see which numbers confused our network. All right. But that basically concludes our running of this network with an artificial neural network for this image data. Coming up next, we already know a little bit about the motivation behind the convolutional neural network because we saw that this particular model had a lot of parameters, over 100,000 parameters. Let's actually learn some of the ideas behind the way a convolutional neural network works, and then we'll be able to tackle this same data set with a convolutional neural network, compare the number of parameters, and then also compare performance. Okay. Thanks, and I'll see you at the next lecture.